Unit 11.4 is ratios of perimeters, areas, and volumes of similar figures. Now, we talked about this in the Algebra 1 book on page 174A. And what we were talking about is scaling up and down. This concept of similarity and proportionality is the concept of scale, the concept of dilation. It's the concept of proportionality. And so we have words when we're dealing with that like scale factor. It dilated by factor of so and so, or the scale factor of this triangle, that triangle is so and so. In dimensional analysis, we would say, well, how many inches are in a foot? Well, 1 foot is 12 inches. And when you're dealing with perimeter, we used it to the first power, area to the second power, and volume to the third. So we've already in the last couple of chapters dealt with those units of measure conversions. We just didn't apply it necessarily to similar figures dealing with the ratios of the areas and volumes. But you see, it's the same thing. We're really scaling up and scaling down, whether we're doing units of measure conversions or whether we're talking about perimeter, area, volume of similar figures. The concept is the same. On page 174A of the Algebra 1 text, we said it like this. We called it the drill. We said if the dimensions of a figure are increased by a factor of x, then the perimeter is also increased by a factor of x because it's one dimension. The area is increased by a factor of x squared, and the volume is increased by a factor of x cubed. When we're talking about the scale factor being a ratio of A to B, then we're saying when we deal with the perimeter, then we take that ratio and we leave it the same because the scale of the dimensions is the same as the scale of perimeter because they're both one dimension. And so we would have that to the first power, you see. But then when we go to area, area is two dimensions. So if the dimensions of a figure increased by x, then the area increased by a factor of x squared because area is two dimensions. But if we're dealing with similar figures that are in a certain ratio, their dimensions are in a certain ratio, then their areas will be in that ratio square because area is two dimensions. And volume is cubic units. So if the ratio are the scale factors A to B, then the ratio of volumes would be A cubed to B cubed, just like volume is cubic, and that should have been X cubed. I'm not sure why that didn't turn into a 3. And so we see this similarity between the drill, as we called it, on page 174A of Algebra and on page 301 of the Geometry book. So if the scale factor of a pair of similar figures is A to B, then the ratio of perimeters, since it's still one dimension, is A to B. The ratio of areas, since it's two dimensions, is A squared to B squared. And the ratio of volumes, because it's three dimensions, is A cubed to B cubed. And we see that same pattern, dimension, perimeter, area is square, volume is cube, in the drill that we learned before. Okay, example. In a pair of similar figures, the scale factor is 3 to 5. So what's the ratio of perimeters? Well, it's the same, 3 to 5. What about the ratio of areas? Well, areas, two dimension, so it's 3 squared to 5 squared. We have to square those. And so we would have 9 to 25 for the ratio of areas. Volumes. Volume is three dimensions, and so we would have that same ratio but cubed. 3 cubed is 3 times 3 times 3, which is 27. 5 cubed is 5 times 5 times 5, which is 125. So if the ratio, or if the scale factor of a pair of similar figures is 3 to 5, then the ratio of the areas is 9 to 25, and the ratio of volumes is 27 to 125. Now, 3 to 5 would be what? Little to big or big to little? Well, the ratio of 3 to 5 would be big to little, because it's a factor, and a factor is what you multiply by, and if you multiplied by 3/5, it would make things smaller. If you wanted the ratio of little to big, or you're going from little to big, you're wanting to get bigger, so you would multiply by the reciprocal 5/3. We call going from big to little scaling down. We call going from little to big scaling up. All of those would be called a dilation, which I generally try to spell wrong. When we talk about transformations, we have reflections, translations, rotations, and dilations. A lot of people don't remember what dilation is. That is to enlarge or reduce by a certain scale. And so you're dealing with similarity when you're enlarging or reducing or scaling up or scaling down or dilating. Those words all go together, you see. Okay? Now, we dealt with this on page 174A in the Algebra 1 textbook also, but it says if the ratio of the areas is 16 to 49, then find these other things. Well, we got to remember that we're going to be looking for the base A, B, just like we looked for the base X with the drill on page 174. So the formula for the ratio of areas is A squared to B squared, where AB is the scale factor. So to get A, we would have to take the square root, okay? Basically what we have is this. A squared is 16, B squared is 49, so we could write out an equation, A squared equals 16, another equation, B squared equals 49. To solve, you would take the square root, and we would get A is equal to 4, take the square root, and get B is equal to 7. So the scale factor A to B is 4 to 7. So in a pair of similar figures, if the ratio of the areas is 16 to 49, then the scale factor, is 4 to 7. The ratio of perimeters is the same, 4 to 7. The ratio of the volumes is 4 cubed to 7 cubed, because volume is 3 dimensions. 4 cubed is 4 times 4, which is 16 times 4, which is 64. 7 cubed is 7 times 7, which is 49 times 7. 49 times 7. I forgot. 243? I don't know. 243 jumped into my head, but that doesn't mean it's right. Let's look at that. 7 to the third. There at 343. I knew that didn't sound just right. 343. There we go. So there's the ratio of volumes, ratio of perimeters, scale factor. Any questions on that? So we're using that A to B, A squared to B squared, A cubed to B cubed as a formula, just like we used X, X squared, X cubed as a formula with the drill on page 174 of the algebra book, okay? All right, let's look at the daily work, we've got a couple of scenarios here. We're going to let you do the first one. Let's take a look at the second one. It says in a pair of similar figures, the ratio of areas, well, let's go back to the first one. I'll just get started. In a pair of similar figures, the scale factor is 2 to 5. That's like our A to B, right? The ratio of volumes is A cube to B cube because volume is 3 dimensions. And so we would have 2 cube to 5 cube. 2 cube is 2 times 2 times 2, which is 8. 5 cube is 5 times 5 times 5, which is 125. And you can get the others from that set. When we look at the second set, we're talking about ratio of areas. The ratio of areas is A squared to B squared. So if we want to find A and B, we can say A squared equals 64, B squared equals 81, find our A and B, and then plug them in to get 4, 5, and 6. Okay? Remember that? Okay. Let's look at some of the word problems. 7 and 8. 7 is an odd answer solution, so you could check that out if you were stuck. So let's just look at number 8. It says parallelogram IJKL is similar to parallelogram MNOP. The perimeter of IJKL is 30 and the perimeter of MNOP is 60. If the area of triangle of the area if the area of parallelogram IJKL is 40, then what is the area of MNOP? Okay. Now, write it out kind of like the drill. If the scale, which is like dimension, is A to B, then the perimeter is A to B. The area is A squared to B squared. And the volume is A cubed to B cubed. So this is running the drill here like we ran the drill in the algebra book. Now, it says perimeter. The perimeter of IJKL is 30 and MNOP is 60. So the ratio of perimeters is 30 to 60, which reduces to 1 to 2. That means the scale factor is AB, which is 1 to 2. The ratio of areas is 1 to 2, but area is square unit, so we square that and get 1 to 4. Volumes, we're going to have 1 to 2, but volume is cubic units, so we cube that and get 1 to 8. So my scale for the sides is 1 to 2. For perimeter, if I'm going to do dimensional analysis, I would use 1 to 2 or 2 to 1, depending on if I'm scaling up or scaling down. For area, I would use 1/4 or 4 over 1. Volume, 1/8 or 8 over 1. Now, depending on if I'm going from little to big or big to little, it says area of IJKL is 40. What is the area of MNOP? Now, IJKL was little. MNOP is big. I'm trying to go from little to big, and I'm going to do so using my area scale because I'm talking about area. So I take what I start with, if you remember the way we do dimensional analysis, we're going to take what we start with times our scale. So we started with the area of the little one, 40 over 1, and we're going to multiply such that we go to the big one. If we're going to go to the big one, then we're going to scale up. If we're scaling up, then we use the large version of that 4 over 1 instead of the small version of that 1 over 4. And so we're going to multiply. We get 4 times 40 times 4 is 160. And so the area of the larger parallelogram would be 160. Any questions on Unit 11.4?